So before we start to look at some more complex logic gate circuits, let's just deal with some of the basics. So here we have two switches and they are A and B. Now when we have an arrangement of two switches, there are four possible combinations of those switches, four unique combinations. At the moment the two switches are set to off, so they are 0 and 0. We can of course turn one of them on. So now we have A, that is 0, and B, that is 1. We can swap that around so that we get A, that is 1, and B, that is 0. And we can turn both of those switches on so that A is 1 and B is 1. Okay, so let's put that into an AND gate. So I'm just going to delete these connections here, and I'm going to get an AND gate, connect these up. So this output now over here we'll call P. Doesn't really matter what you call it, but we're going to call it P. And P now gets added on to my truth table. So let's have a look at the effect changing A and B has on P. So this is of course for an AND gate. So with both switches off on A and B, we can see that P is 0. What about when we switch B to 1? Well, A is 0, B is 1, but P is still 0. And what about when we switch B to off and A to on? Well, we've got A is on, B is off, P is still off. However, what happens using an AND gate to the output when both of the switches are turned on? So A is 1, B is 1, P is also 1. So that is a truth table for a very, very simple circuit which just consists of an AND gate. Let's take our AND gate out, if we can, and let's replace it with an OR gate. Okay, now the combinations of circuits are still the same. We still have 0, 0, 0, 1, 1, 0 and 1, 1. With an OR gate, if we follow this truth table here, with both of the inputs switched to 0, the output is 0. When B is switched to on, the output turns on also. And if we swap those around, we can see that when A is 1 and B is 0, P is 1. And with both A and B set to 1, P is still 1. So that's a truth table for our OR gate.